This is Knowing the Universe, the History and Philosophy of Astronomy. I'm Professor Impey, Distinguished Professor of Astronomy at the University of Arizona. And in this module, we're studying cosmology and looking at the Big Bang. First, let's consider the nature of space and its contents. Let's look at a little scale model, which in 3 stages will get you from something familiar to the size of the universe. Let's set the Earth to a size of a walnut. That makes it a 1 in 10 million scale model. We're taking the Earth down by a factor of 10 million from its real size. In this scale model, the solar system is all approximate. The moon is a pea held at arm's length. The sun, a 3-meter ball about 100 meters away. And the edge of the solar system, Neptune, is another pea 2 kilometers away, 1.5 miles. The nearest star on this scale is 50,000 kilometers away, not even on the surface of the Earth. And so you get a sense of the enormous distance to even the nearest star compared to the size of the solar system. And to put our feeble but heroic attempts at space travel in perspective, going to the moon, that arm's length distance in this scale model, cost us about $100 billion for the Apollo missions to put 12 astronauts on the surface of another world. And that's an arm's length compared to 50,000 kilometers to get to the nearest star. At this scale, light is reduced to a very slow walking speed. There's no way the universe can transmit information any faster. And so we can convey the idea of light travel time, because at a walk's pace, the moon is a second or so away, and that's how long it took radio communications to get there. The sun is 8 minutes walk away, which is how long it takes sunlight to reach us. It's 10 hours to walk across the solar system. And indeed, the distance to the outer planets is 4 or 5 light hours. And then it's a year or so to walk to the nearest stars, and they are light years away. We see them as they were years ago, not as they are right now. Let's take this to the next scale by reducing the scale a factor of 100 million again. The solar system now shrinks to a grain of sand, and the distance between the stars is about 10 meters. So we can imagine the Milky Way as an object about the size of the continental United States, with grains of sand separated by 10 or 15 meters, and the Milky Way with 100 billion of these stars. A phenomenal sized object, and that's just one galaxy. We can reduce another factor of 100 million, and finally we get the Milky Way in view. It's the size of a plate. The nearest galaxy is about 10 meters away, M31. And the universe, the observable universe, is the size of the continental United States again, with billions of galaxies within a 3-dimensional space. These 3 factors have taken us 23 orders of magnitude, a 1 with 23 zeros, and that's what it takes to bring into view the visible universe, starting with something familiar like the Earth. What about space itself? Well, space is actually incredibly empty because, as you imagine, with the grains of sand well separated or the peas well separated in space, most of space is a vacuum. The 1-inch cube of air in your breathing is 10 to the 20 atoms. That's 100 billion atoms. On average, the density of the universe is a factor of 10 to the 22 times lower, 1 atom per cubic meter. What does that mean? Well, imagine stretching that 1-inch cube of air upwards all the way to the Andromeda Galaxy, a couple of million light years away, and that's what it would do to space out the air you're breathing to the mean density of the universe. An incredible vacuum, almost nothing. Let's look at the known universe, starting from the Tibetan Plateau and are working our way out to the subject of later discussion, the microwave background, the radiation relic left over from the Big Bang itself 13.8 billion years ago. And all the objects in between, the solar system, the nearby stars, the Milky Way, and the galaxies out into space, hundreds and then billions of light years away. And that's the end of this topic.